Morning, everybody. I posted the topics this morning, right? So I pulled these topics directly off of my database for the questions that went into the test, right? So let's just start with, what are your questions about maybe what I mean by any of these topics? This is just kind of to help you focus your studies, right? Yeah.
Do we know any Coulomb formulas?
No. That was last unit. I wouldn't go out of my way to.
So all the formulas in this unit then?
Yeah, right. Okay. I mean, circular motion of a charged particle, there's equations for that, right? Magnetic field of a current carrying wire, that could be straight or a loop of wire. Force on a moving charge. Now that one says conceptual. So part of my hesitation with putting these topic lists out. I mean, force on a moving charge conceptual. Could a right-hand rule be in there? Yeah, obviously, right? We did a whole right-hand rule that was a handshake, right? And then Lenz's law conceptual. Are there right-hand rules in there? Yes, right? So like that's two direct call-outs to things that are going to involve right-hand rule. But does Faraday's law potentially need right-hand rules to do? Magnetic field of a wire, does that need you have the crossed wires on your homework and you need to know whether to add or subtract the fields, right? So it's not that those are the only two right-hand rule problems. Right-hand rule can crop up in other situations. So just be aware of that, right? The good news is that there's no right-hand rules in RLC circuits or transformers, right? So, yeah, and I put that note down there. Any questions about the topics? Does this kind of thing help or just scare you? Helps, all right.
For the circular motion of the charge,
Yeah.
Is that going to be more the F equals QVB sine theta, or
Well, it involves that.
mv squared over r1?
Those are the same.
Okay.
You had to do both of those things to get the mass, the result that we had. It was the cyclotron, the movement. We talked about cyclotrons. We talked about the mass spectrometer. We applied our equations in both of those examples. So, did I answer your question? Okay. Anything else here? All right, and then before we get to your questions, yesterday in our lab grasp, there seemed to be several people had an aha moment when I told them there are really only 4 choices when it comes to Lenz's law, in terms of increasing into, out of, all that kind of stuff, right? So I just want to, I know Lenz's law is causing a lot of problems. It always does. There's so many things going on in there, right? But I just wanted to outline this. I thought I did it in class. Maybe I didn't. I'd have to go back and watch my own YouTubes. But what are there's really 4 possibilities for how flux is going to change through any loop, right? It can increase, and then I'm going to use the word into. It can increase out, or it can decrease in either of those directions, right? I mean, we can change into or out of. It can be left or right, up or down, but there's always some direction that the magnetic field has, right? And so what we have here, right, is the change in flux, right? Is that flux getting bigger or smaller, okay? And then we have the magnetic field, right, that is causing that change in flux. And then separate from that, okay, is the loop's response, okay? And this is where Lenz's law comes in, right? So again, really only 4 choices here. And they are much easier because what's the only word you can use in Lenz's law? increase. Lenz's law can only make magnetic field and flux, which is what that word increase means, okay? So what's the opposite of increasing into? Increase out. What would be the opposite of increase right? Increase left, right? The point is that on the two increase ones, it's reversed, right? Whatever your direction was for the increasing flux, you pick the opposite direction for Lenz's law for the new field that's being made by the coil. Okay, so how do you fight a decreasing into? If the only word you can use is increase, then you choose the same word, right? Okay, so what would be a decreasing up? Increase up, right? Do you see what follows there? So into or out, left or right, up or down, that totally depends on the situation. And if you looked at those like practice Lenz's law problems I gave you, they gave you all kinds of sort of different things that were happening, right? But in the case of Lenz's law, when you're applying this, right, if your magnetic flux is increasing and you have the direction for that increasing flux, you pick the opposite direction for Lenz's law. But if the flux is decreasing, you pick the same direction. That's what Lenz's law states, in that it fights the change, right? It fights increases by going opposite. It fights decreases by keeping it the same direction. So did I do this in lecture? Did I? Okay. So I touched on it. Okay. So just they're really some people yesterday were kind of like, oh, there's so many choices. Actually, there isn't. Right? That's it. That's the whole number of choices. Where it's difficult is not only do you have these choices, but identifying the change in flux in the first place always seems to throw people. I can see it right away because I've practiced it for 24 years, right? But like it can be difficult. Like flux is one thing, but then how is it changing, right? We struggle with that concept and idea of something changing in time. And so that's difficult. Getting this right's difficult. And then the multiple right-hand rules that sometimes need to be employed to be able to figure out what's going on can be difficult. So it's hard. It's hard. Okay, what are your questions for me? What are some things either you want to practice or get clarification on? Sky's the limit. I will not answer questions about early European literature of the Middle Ages. It's not a field of expertise I have. I do, however, have some expertise in the growth and ecology of giant sequoias. So if you want me to talk about that, I can. Yeah.
Can we go over the handshake rule?
Yes. Right. And I don't know if do I have the chart that I made up? Remember what chapter that was in? Should have been chapter, was that 22? Was it 21? 20. Oh, you're right. It was 21. 22 was Faraday's law. Where did I put it? Where did I put it? Right there. Okay. Again, this helps my brain sort of organize things, but the question specifically was this handshake rule here, right? And the screen shows you like kind of what to pick for the different parts of your hand. Did you want to like do some practice with that kind of thing? Okay, so let's do not here. Do I carry this over? Yeah, we'll copy this over. This one. Come on. All right, so let's Give me a direction. In, out, left, right, up, down. Left. Velocity or field or force? Velocity. Okay, so the velocity of a positive charge is to the left. Give me in, out, or up, down. Up. A magnetic field is pointed up. Okay? Everywhere in the page, not just there, right? So what's the thing we can find? Force, right? Force is the thing that's missing. So what do we do with our thumb? Goes in the direction of the velocity, which is pointing left, right? And then what do we do with our fingers? They go in the direction of the magnetic field, which would be up. So which way is the palm pointing? In. And how do we indicate in? Yeah, we do that with a X, right? So the force on this particle would be into the page. It's a positive. I said it was a positive charge. Right. If it's negative charge, we flip our answer. And we're done. All right. I really need like a magic 8-ball kind of thing. Right? I was just hoping Google would randomize it for me. Let's see. Our choices are velocity, field, and force. We can have, but there's 6 choices for directions, right? So if this was a 1 or 4, a 2 or 5, now I'm getting distracted, a 3 or 6, and then in, out, up, down, left, right. This isn't going to work very well, but we're going to try it. What is it? Okay, so I got a 5. What is 5 equal to? Field, okay? And then, roll again. 4. So down. Field is down. So down. So yeah, I'm just trying to get this randomized. 2, what's 2? It's also field. Can't have a 2 or a 5. 1, velocity, and it's 2, out. So velocity, we'll make it a positive charge. Velocity is out. What are we looking for? Force again, right? Okay. So what do? We take our thumb and go which way with it? Out, right? And then the field has to go which way? Down. And so my palm is now pointing which way? Right. You're right. We all in the same direction, but it looked reversed to me. All right, so the force was to the right. Should we keep playing? A 6. That's force. Its direction is 5. Left. So a force to the left. You know what? I love getting my steps in. We're going to do this. All right, so what did I say? A force to the left. Force pointing to the left. Okay. Followed by a 1. That would be velocity. Pointed, can't go left. Well, it could go left. If the velocity and the force were left, what would the answer be? 0. Okay. 1 is in. So the velocity of a positive charge is in. Okay. What are we looking for? Now we're looking for field, right? So what do we do with our thumb? We put our thumb into the screen, right? And then the other thing we know is the force. And which way should the force be pointed? Should be pointed left, which leaves my fingers pointing which way? Down. So the magnetic field is down. Oops, green color. So now in my head, I'm writing the Python code for making the app that would do this and quiz you at random with all that extra time I have. I wonder, oh, I bet you ChatGPT could just do it for me, right? Write me a app code for random, anyway. Probably Claude would be better at it. All right. Let's do a negative charge one. Okay, so 2, that's magnetic field, right? And up. So magnetic field is up. The velocity is right. This is a negative charge. Okay. What direction is the force? So we take our V, put it to the right, we put our fingers up. My palm is now facing out, but because it's a negative charge, my answer is inward. Okay. Force was purple. Did I answer your question, Phoebe? Okay. You're welcome. Yeah.
Can you help me go over circular motion of a charged particle in magnetic field?
Your book's equation I had it written down right here. The radius of a circular path that a charge would take in a magnetic field is equal to mv. They use absolute value signs around the charge because we get the direction from the right-hand rule. More on that in a second. Times b, right? Okay, so there's the rate. So like if we have, I don't know, magnetic field pointed into the screen, okay? And let's, clockwise or counterclockwise? Counterclockwise? So let's say we've got a particle that is going around in the counterclockwise direction, right? Circulating around in that magnetic field, okay? So we can calculate the radius of that circle, right? If we know that. So what if this were a proton? What mass would we put in? Not 1. It would be the mass of the proton, whatever that is. I don't know it off the top of my head. I don't care. If I gave you a proton on the exam, I really hope I put the proton's mass on the exam. And if I didn't, what are you going to do? Suffer in silence. No, you're going to just ask me, right? And I will write it on the board, right? I make mistakes on exams. If it was an electron, what would I put in? Mass of the electron. How do we know Like, how do we know if this is an electron or proton? If you were told, okay, find the radius of that circle in this picture, how would you know whether to use the mass of the proton or mass of the electron? You have to use a right-hand rule to find out. There is a force that's acting on this particle as it circulates. What direction are forces for things that are going around in circles? The answer is centripetal, towards the center, okay? Anything moving in a circle has to have a force, and it really doesn't matter where you draw it, okay? But it has to be pointing towards the center, right, of the circular motion, okay? So at the point where I drew that force acting right there, the velocity is that direction, okay, tangential to the circle. Okay, so we know the direction of the force, we know the direction of the velocity, and we know the direction of the field. So we can use a right-hand rule, but we know everything here, Mr. Balogh. Let's find out if this is a positive or negative charge, right? Which way do we put our thumbs? Up in the direction of the velocity, okay? Which way do we put our fingers for the field? In. Is our palm pointing in the direction of the force? Towards the center of the circle? Yeah, right? Kind of no matter where I am on the circle, my fingers will always be pointing in, right? And my thumb will be tangent to the circle. Is my palm like always pointing towards the center? Yeah, okay. So is this charge positive or negative? It's a positive charge, okay? Has to be, because it's circulating the correct way in the magnetic field, okay? What if we had a different charge somewhere else that was circulating the opposite way? This is a positive charge. So if it's circulating the opposite way, you can, again, pick any point on the circle. I'm not sure why I made it so small, but we'll just do down here, right? The velocity is to the left at that, clockwise rotation there. So again, I put my thumb in the direction of the velocity. I put my fingers in the direction of the magnetic field. But now do you see my palm is pointing down? And which way does it need to point for this thing to circulate? Up. And since I have to turn my hand over, what does that mean about that charge? It's got to be a negative charge. So probably an electron, right? Okay. So they don't necessarily have to be protons and electrons. They can just be whatever positive and negative charge, right? But a really mean problem would be like, well, calculate the radius of this thing, right? And you're like, but what's the mass? What's it right? I'd have to tell you the mass of the charge if it was an electron or a proton. And then you'd have to determine which charge to put in there. Anyway, lots of different ways to ask that one. But if you know the radius and you're asked to solve for the mass, what do you do? Yeah, you do some algebra, right? I could give you radius and mass and field and charge and ask you to solve for the velocity that, right? There's I can ask for kind of anything in that equation, right? But that's the kind of master equation for any charge in a magnetic field. That's how it will circulate. That's the radius of its circular path, right? And then I gave you the way to figure out whether or not it's positive or negative just based on the way that it circulates, right? Use the right-hand rule, and if your right-hand rule isn't turning out correct, it's a negative charge. Did I answer your question, Truman? Okay.
So,
Yeah.
just to clarify, when you explain the velocity, you changed it from 2D to 3D when you kind of described the vector moving, the velocity vector that's tangent to the
Mm-hmm.
circle.
Mm-hmm.
And so if we use our right hand for the one on the top left, which is clockwise, you're saying the force, the V is like the thumb,
Mm-hmm.
and then the force is, if it's coming out of the back end towards the center, because it's always going to be centripetal
Mm-hmm.
for something moving in a circle. So if it's coming off the back end of our hand, which doesn't work with the right, we know it's a negative
Yep.
the charged particle.
Right? Because the right-hand rule tells me the force should be down. If that velocity is moving to the right, right? At the top of that, just to add confusion maybe, at the top, which way is the velocity pointed? To the right. It's got to go around in a circle, right? But which way is the force pointed? Which is down, right? So now I use the right-hand rule at the top. V, B, my palm is still pointing in the wrong direction for that force. So I know it has to be negative. Yeah. Kind of doesn't matter where on the circle you decide to do it. So. This is how we tell the difference between when we get to nuclear physics and we have to tell the difference between alpha, beta, and gamma radiation. They determine the difference because they would curve opposite directions in a magnetic field. So one of them is positive, the alpha particle is positively charged, and the beta particle is negatively charged. So you can detect the charge of a particle just by which way it goes in a field. Gamma rays went through and didn't even care if the magnetic field was there. So what does that tell you about the charge? Yeah, no charge. Turns out the gamma ray was a photon. Yeah.
So no force on currents in a magnetic field.
Yeah, I might have like called that out, right? I would have put that as a topic, right?
And same for current carrying wires.
Right. I have the magnetic field of a current carrying wire. That's not what you're referring to? You're referring to the force on a wire, force on a charge. I would have called those out sort of directly. I only have 7 questions I can ask, right? So I probably was trying to decide between circular motion, force on a charge, force on a wire. And it looks like I decided to move the force on a moving charge to a conceptual question and then do circular motion. Maybe I should start rolling dice and making up your exams.
No, I like this.
Yeah, no, just assign a 20-sided die to all the topics that could be on the exam and just roll. No, you don't like that? Get ChatGPT to give me random questions, and I'll just throw that on the exam and see what happens.
I don't remember seeing a transformer problem on the homework, so can you go over transformer?
There was a
There was?
wasn't there one that said like find the ratio, the number of turns?
Oh, okay.
Yeah.
Can we go over one?
You were scaring me there for a second. I was like, I didn't assign homework on that, and I put it on the exam. We're gonna lecture really quick on this. Transformer. Since this apparently is a random choose your own adventure day, let's just ask Google. Random number. Number between 100 and 101. And let's go up to 10,000 and 1. So if 101 is the funniest number, then is 10,001 a lol? Thank you for laughing. Okay. 2,366. And is that the primary or the secondary? Primary. Number of turns in the primary. What number did I say? 2,066. Okay. So Google, what is the number of turns in the secondary? Generate. 3,825. I'm not sure why I didn't just pick numbers that were easy to divide, but there you go. Okay. If the number is bigger than 5,000, it's going to be the voltage in the secondary. And it's less than 5,000, so the voltage in the primary is going to be, let's just do 120 because it's what the wall does. Okay? How do we calculate the voltage in the secondary? I don't remember the equation either. Something divided by something, right? Where is it? Not there. Ah, your book said this. I think I had a slightly different equation, but this works. Okay, so we're looking for voltage in the secondary, right? So I solved this. Voltage in the secondary is going to be equal to voltage in the primary times this ratio, which is going to be 120 times, let's do this right, 120 times secondary 3825 divided by 2366 equals, please detect that. Please detect that. It didn't detect it. 382. We could have done it faster on my phone. 2, 3. See what AI does for you. Nope. Nope. It refuses today. What'd you get? 194. I like it. Volts, right? Now, now it detects it. All right, 194 volt. So, okay, let's pause for a second. The number of turns in the secondary was bigger than the number of turns in the primary, which means this is a step up transformer, right? So what do we expect the voltage to do? Go up, step up. Okay, so we went up, right? So this is the answer to the number of turns. Okay, so now how do we figure out the current in the secondary? It's the inverse, right? Okay, so the current in the, so your book writes current in the secondary over current in the primary is equal to number of turns in the primary, number of turns in the secondary. See how that ratio is flipped over there, right? So if we solve this, current in the secondary is equal to current in the primary, and P over NS, right? I didn't give you the current in the primary. Let's say the current was 10 amps. Primary was 2366, secondary was 3825. Oh, does anybody else get it before I even open my calculator? I got 6.19. Yeah.
What's the unit for this?
Amps. The number of turns just turns out to be a unitless value, right? It's a ratio. So whatever you're working in volts or amps is what it comes out in. So let's see, does that make sense? If the voltage goes up, what should happen to a current? It should go down, right? Like they're yin yang, they're opposites of each other in a transformer. To answer your question, Truman?
Yeah, I just forgot the right on my notes.
Because this is pretty much it, right? Like I think, what are the operative equations here? It's this one and this one, right? Once you have those two, if you're careful, right? Some people did ask me, like, hey, Mr. Balogh, how do I know which side's primary and which side's secondary, right? The primary side is like always the input side, like this is the side that electricity is flowing into. I mean, they could tell you like the output voltage of a transformer is 5 volts, right? What's the input voltage? So if they tell you the output voltage, what is that? Secondary or primary? Secondary, right? Input voltage would be primary side. I generally tend to think of it as like wall side, right? The part you plug into a socket, right? And then a like output to a device of some kind. That, you know, you could have transformers that are not plugged into the wall. But Most of the time, our experience is with the wall side. How is this making you feel? Like, are you nervous? Like, or is this going over this stuff helping like cement a little bit? Yeah. So like sometimes people give me feedback. Well, Mr. Balogh, why didn't you just do the exam, the exam review first, right? Well, the reason you start feeling okay during like this process is because you've already heard it once, right? And now we're summarizing and reinforcing it, right? And then what's the trick or hack that I do to get your brain to do that again? I make you do a cheat sheet. I don't make you, but I tell you that you can have a cheat sheet on the exam, right? What are you doing as you develop that cheat sheet? You're looking at the stuff again, right? Okay? It's almost like repetition is what helps. How do you train for a marathon? You run a bunch of little races, right? Your brain works the same way.
Is step up and step down change how you solve the equation?
I mean, step up and step down just tells you the ratio of the turns.
Oh, okay.
Like if it's a step up and step down always refers to the voltage. So I just know that a step down transformer is going to lower the voltage, right? So that's what it refers to.
On the right side where you put equals 120 and then like a parenthesis, is that just you finished it on the left side to have more room?
Oh, I was trying to get the AI to calculate for me on the page. But yeah, this would be 3825. These AIs are so smart. Why don't they automatically pick the colors for me? All right. So yeah, that would be I just started writing. I tried to write it in clearer numbers so the computer could read my writing. My son went to college 3 years ago, and he got an iPad to help him take notes, and his handwriting was almost as bad as mine, like in high school and stuff. And he said that the iPad helped him write clearer. It was like, how? Like, is it just like taking your handwriting and cleaning it up? He was like, no, but if I want to do calculations in the sheet, I have to write cleaner numbers. So, yeah. There's some really fascinating research that's been verified more than once that students who write notes in class perform better on exams than students who type notes in class. There's something about the hand, pen, and they discovered it didn't matter if it was actual paper or like a tablet where you were handwriting, right? But like in classes where it was like history or English or philosophy or something, they were studying the effect of like laptops in class, right? And a lot of students who were just typing notes on their laptops as the teacher talked, right, ended up on average performing less on exams that involved recall of information. In physics, we've been writing on surfaces since cave walls. So you don't really type physics. You can. Physicists invented a programming language to do it called LaTeX. LaTeX, L-A-T-E-C. T-E-X, sorry, T-E-X, LaTeX. We pronounce it LaTeX. But it's it predates HTML. And most people aren't aware that physicists invented HTML, which is the language of web pages on the internet. They developed LaTeX to be able to typeset mathematical equations for journal articles. So like we code the equation and then the compiler takes it, and instead of us like having to do like manual footnotes or bibliographies or stuff, we just tag things like this is an author, this is an equation, whatever, and then it typesets it for us. We don't even think about it. We just run the code through the compiler and it just dumps it out in a standard format. They took that idea and carried it over to HTML. Like this is a tag, this is a link, this is a bold, this is whatever, right? So that they could share information over the internet. I don't know why I just gave you a history lesson, but there you go. You're welcome. Added extra. What are your other questions? Yeah. Practice on lenses law. Should we do the random Google thing here? Okay, let's see. We need a decision matrix here. For lenses law, we could do in, out, up, down, left, right, right? So that could be all the directions the magnetic field is pointing, right? And then, well, for now, let's do loop is moving, field changing. We'll do 1 through 3 and 4 through 6. Okay, so let's roll the dice. 4. What's 4? Down. And is it a loop or a field? It's a field. No, it's a loop. Okay, so the field is down in that direction, okay? And the loop is, so we got downward field everywhere. And the loop would have to be oriented. This is where I have to use my physics. The loop would have to be oriented like that. So that's supposed to be a 3-dimensional loop. Can you see it? No? This is like the part that's closest to us, and then this part's further away. Okay? All right. And then said the loop was moving, so I'm going to left or right? You guys pick. Left. So the loop is moving to the left. Okay. First step in lenses law, step number 1, right? What do we determine? The flux, right? Is it increasing or decreasing? If that loop moves out of that field, that's a decrease. Okay? Which way was the magnetic field pointed? Down. Okay? So, second step, the opposite of a decreasing down is an increasing down, right? So in the third step, I apply the right-hand rule to this word, right? The word, the direction that you get in step 2. So, which right-hand rule? Hitchhiker. Take our thumb, because the loop is making a downward field to fight the change, okay? And with a downward field, I have current that's flowing from right to left at the front of the loop here. Current flows this way. Was that too weird? Too random? Let's do another one. Let's see what happens. Sometimes dice rolls aren't the best way to do it. 2. 2 was out. So B field is out. Out is dots, right? Okay. Roll for me. Got a 5, so the field is changing. 1 through 3, it's increasing. All right, so it's increasing. So B is increasing, and the loop is sitting still, not moving. So, first step. Increasing or DC. What's it doing? What's the flux doing? Is it increasing or decreasing? Why is it increasing? Because the field is increasing. Okay, so increase. What direction? Out. So what's the response? Increase into. And so right hand rule. Which way are we going to put our thumb? Out or in? In. We always do the second one, right? In gives me a clockwise current. All right, roll the die. 5, left. So the field is pointed to the, that's the right. Pointed to the left. So there's my field. Which one's moving? I got a 4, so that means the field is changing, okay? And 1 through 3 is an increase. It's a 6, so this is a decreasing field with the loop oriented like this in the field. Increasing or decreasing flux? Decreasing? Wrong. Flux is 0. Why is the flux 0? The field goes into and out of the loop. This field line entered and then left. What's the flux? 0. The total sum of in and out. This doesn't work when you orient the, that was a trick. By the way, I threw that in there. So I got to orient the loop. The other orientation would be like that wouldn't work either. Because again, field goes in and out. Really the only way I can orient this loop is like that, right? Where, I don't know which side is forward. This is the forward side. This is the back side. Okay, so here we'll take a page out of that other practice I gave you. So that's like the front. This is like the front side. Okay. So flux increasing or decreasing? Decrease. Which way? To the left. Field's pointed to the left. So we're going to increase to the left. So we're going to increase left, which means that the current will flow up this way and down that way. There's no, with the hitchhiker rule, right? Where you're finding magnetic fields of wires or loops like we're doing here with Lenz's law. There's no like reverse it because it's a negative thing, right? The reverse because it's a negative charge, that only applies to the handshake, the force rule. This randomization didn't work as well because you do have to pick the orientation of the loop with respect to the field. If you guys are going to make these up on your own, make sure that your area vector of your loop points parallel or anti-parallel to your field. That's the only way you get flux through it. You don't understand what that means, don't worry about it. Yeah.
So if velocity and magnetic field are going the same way, it'd be zero.
So like, if this were moving this way, no, not necessarily, because if it enters the field, right? Like if the field were contained to like just this area and it went in, it would go from no field to some field. Yeah. If it's not moving at all, so this is an example of the coil not moving, right? So the field was changing here, right? Again, you just need any change in flux. And you can change the flux by changing the area, changing the strength of the magnetic field, or changing the rotation or orientation of the loop. So just chilling in there. How do you get zero? Zero flux. Zero change in flux. So coil not moving, field not changing would be the only way to like have it be zero if it's just chilling. But it can chill, and then the magnetic field can be wacko. Right, yeah, the field would have to continue to change. Yeah. It's got to change in time. Other questions? What have we practiced today? Stop. Did that. Magnetic field of a current carrying wire. Do I even remember what those I did the almost the same in my brain, so I have trouble. It was it was mu naught over 2 pi little r. Which one's that one? This is the straight wire. And then mu naught I over, is it just 2 big R? Haha. Well, number turns. You can throw number turns. Well, you can't do it in the straight wire. So you are correct. We should put number turns in there. Number of turns. Okay, this is loops. I would have told you if it was a magnetic field of a solenoid. Yeah, that's about it for that one. And again, these are both hitchhikers, right? To find directions. Thumb is straight wire for the straight wire, and fingers are current for the loop. I didn't say that very clearly. Your thumb is the current for a straight wire. Your fingers are the current for the loops. Faraday's law?
Did you say the thumb is the current for straight wire and the fingers are the current for loops?
Yep. Just like our table tells us. Those are my hands, by the way. I held my phone up. I took a picture of my hand and told the software to cut everything out except the fleshy bits. It said, okay. So in the flux, right? The change in flux, that change can be applied to magnetic field, area, or angle. Pick one. Well, whatever one the problem tells you, right? And I think the two on the homework, the two things that were, you saw in the homework were B and A, right? So don't worry so much about the change in angle. Lenz's law, we did a bunch of that. AC RLC series circuit. So I'm not going to write down all the equations for that one, right? But you've got to know you got to be able to find XL, XC, the impedance, right? For the series RLC circuit. Your circuit could be RL, it could be LC, it could be RLC, right? Just pay attention to what's in the circuit and run the calculations. Ohm's law. Did we miss anything? You would think I would know, but I actually don't.
This is helpful to categorize.
Yeah, the topics are not listed on the exam, right? So you can bring this list with you and line them up if you want, but 7 topics, 7 questions. Slightly favoring chapter 21, it appears. Guess it could have been worse. I could have given you 2 Lenz's law questions. Any other questions? Yeah. What's that? Can you write on your hand? Tell you what, you can write on your hand if it involves the right-hand rule. Okay? But you can't write anything else. As in, the answer to number 3 is, and then you put your palm up and wave it around. Right? Speaking of which, physics gang signs being what they are, I'm going to ask you on Thursday to try really hard to keep your right hands to yourselves. Right? Okay. I know you're all sitting in the same room. I know you're sitting next to people, and it's like impossible to not watch somebody do a right-hand rule, right? But like, try to keep your eyes on your own paper. Okay? If I see too much of this going on, right, and other people are like, I'm gonna be like, knock that off. But yes, you are allowed to do the right-hand rule during the test. What's that? Yeah. So, but yeah, do try to do it. There is a magazine. It's called Physics Teacher Magazine, and it's as dull as you think it is. But on the back cover, they often had some sort of joke or clever thing to figure out. One issue had a picture of a bunch of students in a classroom, and there were 2 questions. It said, where in the world is this, and what test are they taking, right? And so I got both right, but all of the students were in some form of right-hand rule. They were all like into the test, but they had their right hands out and they were doing something with it, right? So the obvious answer is they're doing a test on magnetism, right? Like right-hand rule. It's either that or torque, right? Probably magnetism, because Everybody looked really stressed. The location, I got right. I think it was the Netherlands, because the proportion of red and blonde-haired people in the picture was too high. Right? It was just a bunch of Vikings doing the right hand roll. My uncle once gave a lecture in Japan. My uncle was a geologist, and he gave a lecture in Japan to the Japanese Geological Society or something. And he was speaking through an interpreter, and he was talking about magnetic fields in the Earth's crust and all that kind of stuff. And the interpreter was struggling with one of the concepts that my uncle was lecturing on. And so he just stopped the interpreter. He said, hold on a second, I think I can fix this. And he just turned to the 200 people in the room and went like this. And everybody was like, right? Because everybody knows it's universal across the world. Right hand rule, twist in the magnetic field, it points this way, right? And then they were all back on topic and the translator continued. So yeah, we argue over this one, the handshake. There's different versions of the handshake rule, depending on which book you use. But all of the hitchhikers are exactly the same. So yeah, this is a very common one. If you don't ask me questions, I'm going to give you silly anecdotes. Good distraction. But if you don't have any more questions for me, you're certainly free to leave. I'll stay here and answer any questions you want. But I will see you on Thursday for the exam.